Hello everybody. Today I want to discuss Autoresearch. So for those of you who don't know, Autoresearch is a brand new repo published by Andrej Karpathy. Andrej Karpathy is a researcher and one of the founders of OpenAI, as well as I think he was like a chief AI officer at Tesla. I'm not sure exactly, but he has had a fundamental role in shaping this industry, and he recently released this repo that I have found to be really, really interesting. Obviously, it trended on social media for a few days, and there were a lot of products that were instantly built on top of it. But the concept of Autoresearch, I think, can be really summarized by this quote here. So he writes, "One day, frontier AI research used to be done by meat computers in between eating, sleeping, and having fun. Synchronizing once in a while, using Soundwave interconnect in the ritual of group meeting. That era is long gone. Research is now entirely the domain of autonomous swarms of AI agents running across computer clusters in the skies. The agents claim that we are now in the 10,205th generation of the codebase. In any case, no one could tell if it's right or wrong, as the code is now self-modifying binary that has grown beyond human comprehension. This repo is the story of how it all begins." So I think this really summarizes essentially what the goal of this, or what the idea of this is. Autoresearch will let you define something you're trying to accomplish. Define metrics that you can measure, like a floor that you can measure against, and define some file or some directory or some environment that an LLM can modify. It then runs this model in a loop for whatever amount of iterations that you want, and every single iteration, it'll try to make very minimal changes to that code or whatever it is that you're trying to change. It'll run the tests against those validation criteria, and then if it's good, it'll keep it and it'll iterate from there. If it's bad, it'll throw it away and learn from it and move on to something else. And they do this in the sense that it seems like a Ralph loop or similar to a Ralph loop. So for those of you who don't know, Ralph loops are a way to get models to run perpetually, hopefully to do something productive. So the idea is that you think of a spec very, very deeply beforehand, you write it down, and you have validation criteria, and then you run an LLM in a loop, and you feed it the same exact spec over and over again until whatever amount of iterations say that the spec is done, all of the tests pass, everything is good. So it's based on the same idea, but it's more tailored towards research. And in the example that Karpathy had given us, like this is what he was using it for. He states that there are three files that are super important for him in this case. One is program.md, and this is the master prompt, you can think of it, that the model is receiving to understand essentially what to do if it runs into any of X, Y, or Z issues, as well as like what it's supposed to update, how it's supposed to make changes, and then how it's supposed to iterate. So it's a very short document. I think it's 80 lines of code. Yeah, it says 80 lines of code right there. And you have prepare. So prepare is the metrics. So we talked about these metrics. Like, how do you validate that when the model says it did better, that it did do better? Because we know that it's not that they lie. We know that they will just statistically say something incorrect almost all the time. And you need to be the one to essentially steer it back on track. So one of the ways that people have found over the last few years to make them more effective is having validation criteria, test suites that are defined upfront that act as a gate. So the model can't just say that it's done. It has to do the steps within a certain sequence. It has to produce number results. It has to use those to compare against some floor, and then and only then can it actually say that it's done. Or say that it's doing something productive. So in this case, he is optimizing Nanochat. For those who don't know, Nanochat is a repo written by Karpathy. It is GPT-2 level intelligence that you can train on $100 of hardware. I was able to train it at home over 3 days, and this was months ago. At this point, it's like probably 3 times faster. So he set Autoresearch up on Nanochat. There is the file train.md, which is super important. So we looked at the prepare, we looked at the program, and we're also going to look at prepare.md, or what was it? it was train.py. So, and this is the file, and you can think of this as a file or a document or a blog or an article, a code base that the LLM will be modifying in order to helpfully get us closer to those desired metrics. And you can see that here. So he is giving it the file for training the LLM, and he's telling it to go and just make modifications and changes, propose modifications and changes, test them, see if they work. If they do, keep them, iterate from there. If they don't, throw them away. And what he's trying to optimize is the cost and maybe like the amount of VRAM that you need and like all these different things that he's trying to optimize for training this GPT-2 level intelligence on as little hardware and as little time as possible. And he has done a great job. So this Autoresearch running autonomously, the only thing he needs to do is validate the work. But this repo was able to bring down the cost by 10%. I think it was cost or maybe like compute time by 10%, which is very impressive. Like that's like, if you think about like how Nanochat is able to fit GPT to 100 plus billion parameters of intelligence into a single, like I think it was 1 billion parameters on a very small amount of training data, very small amount of compute. That's already impressive. To get that down another 10% is something monumental. It's a monumental effort that they have to take to make that happen. So I was inspired by this repo, and I really enjoy the idea of autonomously researching things. Over the last few months, I have been researching how I can run something like Kimi K2.5 on 192 gigabytes of VRAM. And 512 gigabytes of RAM, and like we could figure out like the rest from there. But the point is, the goal is to take a very, very large model, like this is 1.1 trillion parameters, shrink it down, or at least have a very small portion of the model sitting in video memory. The rest can be in RAM, and then you swap in and out the experts that you need to do computations. Based on how likely it is that they're going to be needed and all that, you swap them in and out dynamically. So that's my idea. It's like either we need to chop off large pieces of the model and lose intelligence, plus quantize it on top of that. So let's say we cut off half of the model. So we have 500 billion parameters left. Then we quantize it to 4 bits. Now we have, so it's 2 trillion, a trillion, it's still 500 gigabytes. Right, like the amount that you need in, so 200, it's still 250 gigabytes at that point. You cut off half the model, plus you quantize it, and you still need 250 gigabytes to run this. And that's not counting the KV cache, the degradation of intelligence, etc. So I have done like a few model compressions over the last year, give or take. You could see them here. Now, I have this, like all of these different models are experiments that I've done with Reap. A few of them got pretty popular, actually. Let's try to see if I can find them. A few of them got like thousands of downloads, but I'm not sure. I don't want to spend too much time on this right now. The point is, so we have these models, and we can do some form of compression to get them to fit on less hardware. But where we end up running into problems is once you have the LLMs and you compress them, they lose intelligence, they lose the ability to do vision, they lose the ability to compute over like data that they haven't seen before, and like it just gets worse and worse and worse the more you do it. So I feel like while that is a viable pattern that you could approach to get this done, I don't like it because I would like to have frontier intelligence at home. I don't want to have like a lobotomized AI running at home. So what do we do then? Right? Like this is my line of thinking. So I've tried like a whole bunch of different things. And the way I do that usually is I go to ChatGPT. I pay for Pro, so I pay for ChatGPT Pro, which is very expensive. It's like $200 plus tax. It ends up being like about $280 where I live per month. But I get access to this model, the GPT 5 point whatever Pro model, and I can ask it questions and I can have it work for very long periods of time. So here is an example from a month ago, give or take. I told it I want to run Kimi 2.5 at home. I gave it like all of the different stats of my hardware, all of the different details, what I've tried, what I haven't. Specifically, like you can see here, this is, we were using something called repo, so we can actually talk about repo a little bit, because I think it is important if you are interested in running LLMs at home. Let's just go repo and hit that. AI. I don't know why it's doing that. So pruning, let's do pruning. Okay, so repo is a method developed by Cerebras that lets you take a model and give it a data set, and then you see what parts of the model are activating. Then you score them and you decide what to chop off, essentially. So it's two things. It's like figuring out what's important in a mixture of expert model, and then cutting it off, right? And so what they found is that you could get 96.7% of the same performance on 50% of the size in a set amount of like things that you're testing for. So you can think agentic coding, or you can think whatever role play, it doesn't matter. So whatever you give it in terms of calibration data, that data that we said you watch and observe to see what is important, what isn't, we give it to the model, and then we see what it does. And then based on that, we can prune parts of the model off. That's what the P stands for. So my idea is, instead of pruning it, let's figure out what matters in the model, and then figure out, so what experts of the model matter, how little of them we can use to get 80% of the way there, and then figure out a way to swap in and out of video memory, so out of the GPUs or mixed memory in the case of Apple, figure out how to swap the experts that we don't need most of the time, but need sometimes. So instead of chopping it off, we keep it there and we fetch those pieces when we need them, and we can evict other pieces to make space for them. So that was the idea. And I've been iterating on this. Before that, I tried like a whole bunch of different 1.5-bit compression techniques, which work pretty well, at least in theory, right? Like there isn't much that we can do to test them, because a lot of this is just research. But let's go down and see. Yeah, you can see these prompts are absolutely gigantic. So I send it over the prompt, and then it goes and it thought for 30 minutes. I've seen it think for like 3 hours before. So this is a decent amount of time. And then it comes back and it, like, we have a conversation about what exactly I need in order to make this happen. Now, router only calibration. Okay, I will get distracted by reading this. So essentially, it comes back to me with like, here's the research, here's what is going on. Get a native like int4 quantization, and then have parts of it here, parts of it there. And so this is good information relatively, because it goes and reads research papers. You can see here, like it's actually reading real research papers. And every single one that I would click on, like I'll just go there. All of them are real. Right? Like none of them are hallucinations, which is what I love about this model a lot. Obviously, like it hallucinates. None of them are perfect, but it seems better. So I will go back and forth with it for a few days. Once I have something that I feel makes sense logically, I will then take it over to whatever, my IDE or my terminal, and then we'll go from there. So here you can see me having a conversation with Droid, and I tell it like, here, I'll copy whatever GPT 5.4 Pro gives me, and then I'll give it information around like, here's the hardware that you need, here's what I want you to do, and here's how we measure stuff. And then we'll set up the loop. So the loop being, what is this? What are we researching exactly? What are those metrics? How often are we running it? And what is our improvement rate, et cetera, et cetera? What is the model actually modifying to make these changes? And so once I do that, I go and I come back and I see, okay, first measured real case, 227. Let's see what it says. So this is the model running and doing the research for me. And what I mean by research here is it took a model called Qwen 3.5 35B. So this is a pretty small model. I can fit this, like I can fit 3 or 4 of these on my machine. But it's easier to test with a small model like this. They're much faster, so we could basically inference them like much quicker, we could get results much quicker, and we can go through the iteration cycles much faster. So I gave it the 3 files, right? Program.py, program.md, results.md, and I gave it the compute that is sitting at home, so my 83090s, and what we've been testing has been like all over the place. We've tried a bunch of different things, but basically I will put the original Qwen 3.5 versus some form of test that I've been running, and I will see 3 things. How much memory do I need? How much video memory do I need? How much slower is this like fragmented dynamic system that I built? And then how accurate is it compared to the original? So these are the 3 most important metrics that we're tracking. Now they have like more scientific terminology and like, specific numbers and how to get them and all that, but those are the 3 things we're optimizing for. And so I've been running this for like, I think 3 days now, and it's just been going and going and going. And you can see here on the right side where we have this blue screen, we can check, okay. So we have here the activations. So I gave it all of my training data. I will take it back and we'll do data extraction. Yes. So I made a repo sometime last year. I think it was in like October or November. And the repo does very little. Like it's super simple. You run it on your machine. It goes into all of the different paths where like Codex will store the chat history, where Claude will store the chat history, Droid, OpenCode, all of these different harnesses, Cursor. And so I extract all of the conversations, all of the diffs, all of the function calls out of those. I make a copy of them, and then I turn it into training data, right? Training data being data that we can use to do calibration, that we can use to fine-tune the model, that we can even use to train like a small LoRa or whatever, on my own history with AI, right? Because I can, like, this is all my conversations with Claude Code and all my conversations with Codex, which is super useful. So I get that data, it's very highly relevant, and then I give it to Qwen, and I see what is lighting up in terms of the experts, right? So a mixture of experts model. Let's try to go back to REAP for a second, because I think if you can get this, it'll make a lot of sense what I'm on about. So a mixture of experts model is, think of a model as a grouping of 50 different models. And then every time you have a token that's being generated, you will activate 2 or 4 or 8 or whatever. And the rest just sit there. So this is way faster because not all of the model needs to see whatever it is that you have. So it's much faster. But the VRAM is just taken up, right? Like you have to have all of the weights on the GPUs, otherwise it'll slow down drastically. And when that's the case, then it's going to be very painful, which is what I don't want. I want to be able to use this as if I were using Codex like 6 months ago, or whatever slow model here 6 months ago. Now, this mechanism here where you see it's like input, the router decides what experts are important and it passes the information over to that expert, and then you get an output. So all these 3 experts, they're useless, right? Like during that specific token activation. So what's interesting is that you don't need all of the experts, right? At least Cerebras proved that on like fixed data sets, you typically only need 50% of the experts. So if you have your own personal training data and you give it to the model, you really only need 50% of it to answer everything. You need 27% of it to answer 80% plus of all of the prompts, and you need 7% of the model, or typically, at least this one. So basically two times the active experts to answer 50% of all the prompts coming in. So we could bring down, technically, the VRAM requirements for a 35 billion parameter model to 6 gigabytes with 0 loss, as long as we are activating and choosing the right experts, and as long as we can swap in and out the right experts properly. So given that we have this idea, we can go back and we can look at essentially what's going on. So I have a mix of both Claude in Droid and then Codex in Codex, doing this research all day, every day for the last few months. So I can look at the main numbers here. Prefill ratio 0.05x baseline. Okay. So you can see here that my method is 2 times slower. The amount of tokens that we are getting is literally half, right? Like it's almost half, because I'm storing 60% of the experts. I think it's like 60, no, actually 70+% of the experts. I'm storing them in the CPU. The rest I'm storing in VRAM. And the tokens a second is relatively decent, right? I think this average baseline, like this is low because I don't think we are optimal. One is I am power capping my GPUs, and then I'm using only one of my 8 GPUs for the smaller version. So average text similarity, this sounds bad, but the sampled outputs are often semantically similar or phrased differently. So right now it's lexical similarity. Okay. Okay, this is where I think it's super important. I'll try to leave up with this. When you have an idea for something that you want an agent to accomplish autonomously, you need 2 things, or maybe you need 3 things. One is proper description of what you want and the metrics that you are trying to optimize for, or the thing that you are trying to bring about. 2, you need proper guidance on what not to do and how to behave, because the LMs will optimize for making you happy. They just want to stop running. Like that's essentially like how it works, right? They just want to say that they're done and move on, or like stop their run. So if you want them to perform like a task over days, you need to build a system where they are just simply responding to mechanical outputs. Like you can't give it to an agent and then expect the agent to run for 3 days by itself, of its own like volition, right, of its own programming. You need something on the outside that forces it to behave in a specific way that you want, and so that's what the deep research thing is, or you know the loop, the Ralph loop. And then the last thing is you need human validation. So when they send you like a prompt like this, what you need to do is read it, and the reason you need to read it is because these things are just not going to tell you what's true. So when it says like it's 2x slower, like do I take that at face value? Because exactly 2x slower just doesn't seem right. Why is it exactly 2 times slower? It seems like a little bit wrong, right? And then how is it 2 times slower at prefill but not any slower at generation? Maybe here this isn't something that is a problem. But when I look at these numbers, I just feel like there's something suspicious, and I need to dig around a little more before I can actually make a good judgment call. I've been running this for days now on end, and I feel like I've made progress, but also I could be completely wrong. I was able to get a part of the model to run, I was able to just construct the model dynamically, but this only really works for smaller models. If you start thinking about like Kimi, I don't think you could do that, right? It's like you're moving hundreds of gigabytes between GPU and CPU, and it's just going to slow down drastically, and it's going to suck. So just fast forwarding for a second, like the reason I bring this up is this is a trend that is going to continue. We're just going to continue having like improvements in the systems. A lot of work is going to be automated. A lot of like knowledge is going to be gained via this asymmetrical automation, where you have one person who's running 15 different research bots that are accurate, and that's like what's going to separate like the good, like the smart people from, or like the successful people from those that don't succeed. Because anybody can just click run, but then validating it and then researching it and like figuring out how to test it, figuring out how to describe what you want, figuring out how to describe it to others afterwards, writing about it, getting attention, productizing it, releasing a reason. Like all of this is skills that LMs that don't really help with. So that's really where I think the edge is right now, is you need to focus on finding something that you care about that works, figuring out how to define what you want to get out of it, figuring out how to automate it, and then figuring out how to validate it, and then figuring out how to publish it. If you can do those four things, I mean, I don't think there's any knowledge right now on the planet that cannot be automated. I just don't. Maybe other people disagree with me. I'm hoping I'm not being too much of a hype beast. I'm trying my best to share this knowledge, and hopefully, if I'm wrong, I can know that soon. Thank you for listening, and I will see you in the next.